Welcome to uh today's today's session. Okay, let me uh welcome. It's part four, right? Yeah, I think it's part four. So we're gonna continue where we left off. So if you check, there's a couple of things that I want to fix. So this is not, yeah, I forgot the term. I had forgotten the term for it, but yeah, it's actually called uh, general association. That's the proper term for it. It's called general association. So we just need to fix that. So let me open my notepad called general association. So if you're looking at the question paper and you can't it's neither what the ones that you're used to. It's neither composition, no aggregation, no inheritance. It's none of those. Then you know it has to be general association. Then what else do I need? Is there anything that I need to fix? Well, I don't think there's anything else that I need to fix. Yeah, I don't think there's anything else that I need to fix. Oh, we still haven't done this question 2.4, 2.5, and 2.6. We still haven't done that, but yeah, we'll get to that. So let us continue with question 3.2. Okay, so 3.2, define a structure with alignment packing or padding disabled to represent the data for one dam. Okay. You may assume that the name of each dam cannot exceed 20 characters and that none of the dams has existed for over 6 years. So when it comes to the dam name, remember that the name, it has to be a string of characters. In this case, we are given a maximum number of characters, so we have to make it an array instead of using the normal string data type. So we have to make it a one-dimensional array of characters. So it has to be char, and then you specify, remember the square brackets, specify the size. Then you give it a name, maybe dam, okay, dam name, something like this. So instead, we're gonna use the array of characters instead of a string. Because with the string, we could use a string, it's fine, but it's more accurate to represent that with a one-dimensional array of characters. Because with the one-dimensional array of characters, you create a fixed size string, or a fixed size in the sense that you can put a maximum number of characters that you can represent. So since you can specify the maximum number of characters, the we're gonna use the okay, I'm gonna use Notepad. Okay. So we're gonna use the the array of characters to represent the string or the dam name. And then as for the okay, none of the dams has existed for over 6 years. So a set of real values, each value represents the water level percentage in, oh, and by the way, I think I represented this as a double. Yeah, I was supposed to use an integer. A real value is an integer. And then a character representing the dam's codified region, R0 to Rn, a set of real values. Each value represents the water level percentage for that dam in 1 year. Um, okay, let me see. I wanna see the I want to see where we can represent the number of years. Okay, the data represents the water levels over a number of years for several dams. Oh, okay, so over the number of years for several dams. So we shouldn't exist. We shouldn't exceed the. We shouldn't exceed 6 years. So basically, when we're reading the when we're reading the information from the file, we're gonna create a for loop that goes from 0 to 6. So it's 0, but it's less than 6, so that so that we don't exceed 6 years. So let's do that. Let's create the record structure. So the record structure is going to represent the data for one dam, right? So I'm just going to call it dam. So struct dam represents information about the dam. So obviously we're going to have the dam name instead of using the string data type, we're going to use an array of characters. So it's going to have a maximum of 20 characters, and then we're going to call it dam name. Then we're gonna have the region, right? Dam region, which is which is a character representing the uh dam's codified region. It's a character. So a character, remember, that's just a char, and then we're gonna call it dam region like this. And then the set of real values, and remember this should be integers. A set of real values, each value represents the water level percentage. So we're gonna need to represent that. So let me see which values output to apply the water percentage. The data represents the water levels over a number of years for several dams. Each line represents the water level for one specific dam. There can be an arbitrary number of dams, and the lines can vary in length, since not all dams have existed for the same number of years. Each dam in a line is separated by a space character, and has the following meaning. A string not longer than 16 characters. Yeah, for this one it was 16 characters, and then because here we're working with the text file. Here we're dealing with the text file. So the question is, okay, yeah, it applies for both. Yeah, as you can see, even the names are similar. Water levels .txt, and this one is water levels.dat. So we're actually working with the same record structure. It's just that we storing it in a binary file and reading it from a text file. So let's see, where's the you may assume that the name of each dam cannot exceed 20 characters, and that none of the dams has existed for over 6 years. Okay. So we just need to define that record structure. So now we need to define these values. So this set of real values, right? 0 to Rn, each value represents the water level percentage, right, for that dam in 1 year. So as you can see here, right, we were not given the information about the number of dams, right? So we are not given not the number of dams, the number of real values, number of how many water level percentages are there in a year. We are not given. So that's a problem. So since we're not given, that means we're gonna need to work with a data type that resizes automatically as you add elements to it. And that data type is going to be what? A vector. So we're gonna use a vector. So it's a vector. Remember, a vector is just an array. It's a one-dimensional array. but it's a one-dimensional array that can resize, that resizes automatically. So it gets allocated dynamically. So yeah, every time you add an element, it increases by 1. So I can show you just a simple example, right? So let's come here and let's create a new file, right? So I'm going to create a new file and call it main.cpp. And then let me say main.cpp. Yeah, I just want to open it here. Okay, so now I have it open. So let's code. Let's make a simple example. But I can even show you like how it's implemented behind the scenes. Just a simple example. So I'm gonna need to include the IO stream because I'm gonna be working with input and output. And then I'm gonna need to include the vector class or the vector file because I'm gonna work with the vector. And then I'm gonna need to create a main, and then I'm gonna return 0 to the caller. So 0, remember 0, it means that the program terminated successfully. So by terminated, I just mean it ended successfully. That's all I'm saying there. So this is how you create a vector, right? So remember the vector, you say vector, this, right? And then you specify the type. So let's create a vector of integers, right? The reason why it's not like showing anything whenever I type vector is because I didn't specify which namespace is it in. It's in the standard namespace. So vector, there we go. Now it's showing me how it is. So you see, I put in the type name, right? There's the type name. So I need to specify the type name. It's basically a generic type. Remember, when you're working with templates, it's exactly like that. That's a vector. So it can take in any type. So let me say I want to create a vector of integers. And then I'm going to say vec values, right? Just going to be a vector of values. And you can just initialize them to 0 like this. So remember, those curly braces, it means everything should be initialized to 0. But if you provide a value first, it's only going to initialize the value at index 0. So yeah, I'm just going to leave it like this. And then we can check the size of a vector by using the size function, right? So you call the instance of the vector, basically the variable of that type vector, and then you call the size function for that vector. And then I think it should build. Let me see. I'm not used to this. Let's see if it's going to build properly. Okay, nope. Let me just build it my own way. Let me build it manually. Okay, so I'm gonna close. Then, okay, it says build was successful, but that's not what I'm looking for. So I'm going to use the G++ to compile it. So main.cpp and create an object file called main, right? Compiled. Then I run the main. You see, then I run the main. Okay, so the output is 0 because our vector at this moment doesn't have any values, right? So by default, it's going to have 0. But the moment I start adding values, it's going to resize. So this was before, right? So I'm going to output here and say this is before, this is before, and then this is going to be after, right? Like values dot size, and that namespace and line. So there it is. So vec values. So how do I add? Use the pushback function. it pushes the value to the end of the vector, or at the end of the array. At this point, there's no value, so it's going to push it at the first index. So it's going to push it at index 0. So let's say I add 10. Then vec values dot pushback add 11, right? So I've added 2 values. So now what's going to happen is that every time I add a value, right, it's going to say size now plus or equals 1, because now I've added another element. Every time I add an element, plus or equals to 1. So now I'm expecting an output of 2. So I'm just gonna build it again, then run it. There we go. So you have before, which is 0, and then after adding those 2 elements, now the size is 0. It is 2. So as you can see, this is why I'm saying we should use a vector, because it resizes automatically every time you have a value, and it's actually used in these scenarios where you don't know exactly how many elements you're going to have. If you knew exactly how many elements you're going to have, you'd create a fixed size array. In our case, we don't know. So I'm going to need to use this vector, and it's part of the standard namespace. So I'm going to create a vector, and then I'm going to say standard and then vector. It's going to be of type integer, right? Remember, I said real values represent integers. So I'm going to say percentages. I'm just going to call it percentages like this. So as you can see, there we go. We have our record structure. And then that's it. That's all we had to do. So we have defined the record structure, right? So I would say maybe we have roughly around 3 marks. We haven't defined alignment padding or packing. So let's talk about the alignment packing, right? Because it's very important. So the way you go about doing it, so it's like this. Let me show the sort of like a demonstration of how this thing works. Which app can I use to demonstrate this? Text editor. Let me see. Okay, this one. Okay, I'm not sure how you use it, but yeah, I'm gonna try and figure it out. So let's see. Insert the display. Okay, these are the shapes. Okay, so this is how it works. So I'm just gonna remove this for now and then zoom in. And then I don't want to see the pages. So let's explain what's really going on here. Okay, let me just leave it like this. So let's explain what's going on. So the reason why I have to do alignment padding, right? So let me explain something simple. So we have 32-bit systems, and there's also 64-bit systems. And then nowadays or recently, there's been talks about 128-bit systems, right? What does this mean? What am I talking about when I say 32-bit, 64-bit? So basically, all I'm saying is that if you have a 32-bit, right, it represents each information in 4 bytes. That's what it does. It represents each information in 4 bytes. And then if it's 64, obviously it's going to represent it in 8 bytes, right? Represent it in 8 bytes, because how do you get 64 if you have 32? You just multiply 32 by 2. So if I have 4 bytes here, I just multiply that by 2 and I get 8. So it uses 8 bytes to represent the information. And then this one uses 8 times 2, which is 16 bytes, right? And remember what he said, 1 byte is equivalent to 8 bits. And we said bits are basically binary bits. It's the term bit stands for binary digits. So it uses 8 binary digits, right? If you have 1 bit. So if you have 4 byte, if you have 1 byte, if you have 4 bytes, that means you can represent 4 times 8 bits or binary digits. That's the number of binary digits you can represent in that 32-bit system, right? So if this is the case, right, if it represents by 4 bytes, this is how it's going to be. This is what I mean by 4 bytes. So let's see. So by 4 bytes, you're gonna have something like this, right? And then copy, right? So it's gonna use these 4 memory blocks to represent one thing. Then it's gonna have another set of 4 blocks to represent the other thing. And then it's gonna have another set to represent another value. So that's how it's going to be representing. You can imagine each cell or each box as like a bit, or no, it's like 1 byte. You can, yeah, let's just imagine like 1 byte, right? So now if it's like this, right? And then let me see if I can insert text here. Okay. Okay, that's too large. Let me see. Format. We have this shape, symbols. Okay. Let me see if I can. Okay, so you can imagine this is like. Let me see. Okay, I don't know why doing that, but okay, we're just gonna have to work with what we have. So you can imagine that the cell, this is like 1 byte of information, right? 1 byte of information, and then you're gonna have another cell, 1 byte, 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 right? So the problem with having to work with the record structure as it is like this, right? The problem with having to work with this as it is, the problem is that you're gonna have to you're gonna have unnecessary CPU cycles, right? So CPU, if you remember CPU, this is just a central processing unit, which basically does the mathematics and loading and processing your apps. So whenever you double click an application on your operating system, this is the brain. It's like it's usually called like the brain of the computer. It's like it's meant for processing things. So the way your computer works is that it takes something from memory. Basically, it's stored in memory, it's saved in your hard drive. Then it gets loaded onto the central processing unit. That's why you can be able to run it. That's why VS Code is open like this. It's running, it's being executed by the CPU. So that's what as I was saying. So the CPU does all of that, right? So when the CPU does all of these calculations and processing and doing the mathematics calculations, all of that, it depends on the architecture that you have that you're working with, or the operating system that you have. If it's 32-bit, you're going to be working with 4 bytes 4-byte blocks, right? So it's going to be saving it going to use 4 bytes to represent one thing. So since it's going to use 4 bytes, so remember that this is usually a data type has a size. So we can even double check the size of the data types. So let's check the size of, you can use the size of keyword, which finds the size of something in bytes, right? Because remember, working with bytes. So size of a character, a char. What is its size? And then the size of the vector, size of, it depends on the number of elements that are there. Yeah, I think it totally depends on the number of elements that are in the vector. So I'm gonna say vec values like this. You'd expect it to say, for example, it has integers, right? It's representing integers, and at this moment it has 2 integers, and each integer is equivalent to 4 bytes, right? So you'd expect it to be like 4 times 2, which is 8 bytes. Sometimes it could be like that, sometimes it's not. It's very unpredictable. So let's check out how it's going to look. So, okay, it didn't even output the size of vec values. Don't know why I didn't do that, but yeah. So as you can see, this character is of size, it's 1 byte each, right? So if it's 1 byte each, and I'm using 20, I'm gonna need to a maximum of 20 characters to represent the name. That means it's gonna have 20 blocks, because remember that what he said, each block represents 1 byte. So I'm gonna need 20 of these. So I'm gonna have 4, 8, 12, and then I'm gonna need to have another set of 4 like this. There we go here. 4, 8, 12, 16, right? And then 20 again. There we go. So I'm gonna have all of these memory blocks to represent the value, the name. So for example, in memory cell 1, you could have in this block, you could have maybe the character Y, right? And then in the other memory block, you could have the character E, right? Until it forms that word that you want. So each block stores a letter, each letter. So that's why I'm saying we're gonna need 20 blocks, because we can store a maximum of 20 letters to represent the damn name. But it's gonna split it up into 4 bytes, right? To keep that in mind. So if it does that, that means to represent this one character, you see, we also have the DEM region. To represent the DEM region, we're also gonna have to create another set of 4. Remember, it represents in 4 bytes. So even if you are trying to represent just one character, it doesn't care. It really doesn't care. So let's say you just want to represent the DEM region. Let's say G stands for Gauteng. You want to represent that, right? So this, obviously, this memory block, these 4 cells here, they'll be representing what? Let me see. Mm, uh, da- 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 da. Okay, I'm not familiar with this tool yet, but yeah, you can just imagine this is gonna, let me just do this. Just put it down here and say this is gonna be the region, right? So this block here, so everything here So everything here, this part is going to represent the region. But then remember, the region is only one character. So now we're going to have 3 empty blocks. Because remember, by default, if you have a 32-bit, it has to represent each value in terms of 4 bytes. So now you have all these empty spaces, right? And even for the thing, for even for the what is this, for the name, you might not use all the 20 blocks. So you might just have even have something very simple. You just want to represent yes. You want to store yes, right? But what about all these memory blocks that are empty? You see, now it becomes a problem. You have all these empty blocks. All these blocks are empty. So what it usually does, right? It would take this and then continue where there's an empty space, and then continue filling up and filling up. So in order to avoid all of these inconsistencies, all of this, the CPU, because it might fill up and try to fill in the information and things like that, and end up having to have to work work twice to represent the same information, because it might happen that by the time it reaches the last block, this one, it hasn't stored every information for one record structure. That becomes a problem. So now it has to restart and create another set of 4 bytes and continue where it left off. You see, you're making it work and work over time, whereas there's empty spaces here, there's inconsistencies, all of those things. So in order for us to avoid all of these inconsistencies, we're gonna do alignment padding. We're gonna align it in such a way that each data type or each variable, it takes up the same memory. So in our case, we're gonna make it take up 1 byte, right? So in order to represent this, let's do it like this. Let me copy this data structure here, right? And do this, right? And then them name. Oh, okay. Let's forget these things. So yeah, I was using the Java syntax. Yeah, you put the the square brackets at the end. So yeah, let's try to find the size of this data type, because remember that each data type has a size in bytes. So we should be able to find the size of the dem type, right? Should be able to find the size of the dem type. So let's do that. Let's run and see. See, it's 48 bytes in memory, and this 48 bytes, it might be something that it might actually make sense. So let's just double check what the size of a vector is. It's usually a vector of, that's right. Let's find the size of that in bytes. 24. Yeah, yeah, nah, it has a lot of bytes. So this is 24 bytes, and then this is 1 byte, and this is 20 bytes. I think it's supposed to add extra 3 bytes. Yeah, right? Yeah, it does add extra 3 bytes. So let's calculate how many bytes would it be? 20 plus 1 plus 24, which is going to be 45. But then the output, if you remember the output, it was 48. So where is it getting 48 from? It usually adds an extra 3 bytes. So that's why it was outputting 48 bytes. But then if we do alignment padding, you're going to see that there's going to be consistencies with our type. Okay, that's fine. So I'm going to put dem here, write that dem type, and then we build it. Then here we go. Okay, why is it? Oh, I haven't saved. Yeah, you don't save, you don't show the changes. That's why I was showing 24. So as you can see, it's showing, if you check here down here, it's showing 48 bytes now. So we are definitely sure that we are on the right track. So let's see now. Let's try to put alignment padding, right? So I'm gonna say that my type, um, but is it pack and then push or push pack? I think I might be. I think this should be fine, right? Yeah, I think this is the syntax. And then you're gonna say hash pragma, um, um, pack again, and then say pop to release the memory. So it's gonna be like this. Then you should now specify you want to pack it in terms of how many bytes. So I want to pack it in terms of 1 byte. So let's see now what the output should be, what the output would be. So I'm gonna do this. Okay, I wanna run main. So there you go. Now it's 45 bytes. So now it's exactly the number of bytes that we're expecting it. So that means it's gonna be everything's gonna be stored in a specific 1 byte container. Remember that we had inconsistencies back then with when you hadn't done the alignment padding. So what happened was that it was adding those extra bytes for no reason. So now it gives you the exact number of bytes that you expected, which is 45 bytes. So and we want that because if we have that, it's going to be very easy to work with this, to work with having to write to the file and reading from the file, because it knows exactly the number of bytes that represent each DEM. So it's gonna see, okay, it's gonna do this, it's gonna come here and see and say, okay, this is a byte, this is a byte, this is a byte, this is a byte, and so on until it reaches the end. So it's gonna count. Let's say this is 4 bytes, right? So if it sees the first four bytes, it'll be like, oh, this is one DEM, and tell the difference because you did do alignment padding so that it knows when when one record structure stops and where it ends in terms of the bytes. It's exactly 1 byte to represent each information. So that means in this example that I'm doing right now, it's going to use let's say 4 bytes. So when it sees another set of 4 bytes, right? Let me copy and paste this. Copy, paste. So when it sees another set of 4 bytes, it'll be like, oh, okay, so 1, 2, 3, 4. This is the first record structure. Then it goes 1, 2, 3, 4. Oh, I've reached the end of the next DEM. So it's very important to do alignment padding. So as you can see, it's going to be very accurate. It's going to, in a way, it's going to be doing this. You see, it's going to be dividing. In a way, it's going to be doing this. Like, oh, this is the first record structure, second record structure, third record structure, and so on, because it did alignment padding. So you just say hash pragma, and then you say pack. You pack it, and then you push it, and then you specify how many bytes you want it to represent. I want it to be exact. So I want to have each value in its own container, in its own box. So if you check this, I want each value to be inside here. So I'm gonna tell it I'm gonna need 45 rectangles or squares, whatever you wanna call them. So it's gonna need exactly 45 to store every single value inside this box. That's what I'm doing now with alignment padding. And you can combine this into one line. So you can say pack one, and then you can come here and say push underscore one. Still the same thing. Then you build it again, you see it's still exactly the same bytes. 45, exactly 45. That's exactly what we were what expecting. So yeah, that's alignment pairing. So this is the answer that you're supposed to write for that question. And it's very important. If you ever see any array of values that you have to read from the file and you don't know exactly how many are they, always use a vector, because a vector, it resizes dynamically. It automatically increases size every time you add an element. So keep that in mind. So that's the answer for 3.2, right? And none of the dams has existed for over 6 years. Oh, okay, I see. Okay, in a way, I'm starting to understand what the 6 years is about. But if they hadn't given you this information, you could just use a vector. But in our case, they're saying each value represents a year. As you can see, they say for that dam in 1 year, they're saying each value represents the percentage for 1 year. And those basically what they're saying is that those values shouldn't exceed 6. So I should create a, I mean, yeah, it's gonna save you a lot of memory if you use, okay, yeah, you should actually do it exactly how they want you to do it. So that means I'm gonna change it to a fixed arrays now, because now I know exactly how many values are there. So it's still gonna be called percentages. Then it shouldn't exceed 6. So it's gonna be like this. So now I know this is going to be 6 bytes. No, 6, not 6. 6 by 4. Um, it's actually the same size as the vector. This is going to be 24 bytes, right? This is exactly what the vector was. But yeah, just for the sake of getting it correct, this is what they wanted you to do. So it should be a fixed size of 6, a maximum of 6. So yeah, I was trying to understand why they're showing that year there. As you can see, as I said, it's exactly the same value, 45 bytes. So yeah, just use, but it's actually very good to show you all the possible ways of answering it. So yeah, I'm just gonna use the way that they wanted me to use, the way that they wanted me to solve it. They wanted me to create a fixed size array of 6 years. So another thing you should be careful of when you're reading, pay attention to what you're reading. Because as you can see, I was confused where the years was coming from. If I had paid attention to this line that says each value represents a year, you can skip the what percentage, but it represents a year. So if I have 7 values, that means it's values for 7 years. So basically what this means is that the array shouldn't exceed 6 years. I shouldn't have more than 6 values. I should have a maximum of 6 values. So yeah, this is how they wanted you to answer that question. And then obviously you need to pop it. Pop is basically, in a way, you can basically saying you're releasing memory. In a way, you can put it like that. Popping is just releasing memory so that you can allocate another 20 or 45 bytes for another record structure. If you don't pop, if you don't do this part, if you don't pop it, it's gonna keep storing and storing and storing and storing nonstop. That's a problem. So we need to pop it and say, okay, that's the maximum. It's 45. So now when you see another 45 bytes, that's for a different record structure. So yeah, this is the solution for that question. This one. This is how they wanted it. This is exactly how they wanted you to do it. And then assume that the file water levels.dat is a pre-existing binary file of homogeneous records of type defined in question 2. So now we are using this record structure to either read and write from the binary file. So let's see. So write code for a function that accesses a DEM by its index. So it accesses the DEM by its index, right? So to see if it access to access the DEM by index, let's see. Yeah, it's good. It's good. It's a bit tricky. That's the thing. If you don't understand what they're asking you, you might get lost and not know how to answer the question. So here they just want you to write a function, right, that accesses a DEM by its index. So basically the function should take in an index to access the to access a DEM by index, and then is a pre-existing binary file of homogeneous records of the type defined in 3.2. Write a function that determines if the number of records from the file is odd. So yeah, we're gonna check the slides and see 3.4 because there's some guideline that you have to follow. So let's check 3.3. So assuming that the file water levels that is a pre-existing binary file of homogeneous records of this type that you've defined here. Write code for a function that accesses a DEM by its index, right? So now I need to write a function, right? So let's say function get DEM, right? Which takes in an index. I have that function that does that. It takes in an index. So the way I'm going to implement it is going to be a very straightforward way. So I'm just going to delete this. Don't save. Okay, we're just going to use VS Code to demonstrate everything. So we have this get DEM, right? So it gets the DEM by its index, right? How do we do that? How do we get it by the index? So it's a binary file, right? So basically I need to read from the file. That's what they're saying here. I need to read from the file. So I'm gonna copy this. Then obviously, when you're reading from the file, you're gonna need to include the file, right? But then remember, it's abbreviated to just F string. F stands for file string. So it's a way to work with file strings, work with files. So have the DEM, right. So what I'm going to do is I'm going to create a counter equals to 0, right? So this counter is basically meant to store the current index of the DEM. It is to store the current index for the DEM. And then I'm going to check if that current index matches with the index that the user wants. Then I know that's the DEM they're looking for. And immediately, once I found the DEM, I'm going to exit. I'm just going to break from the loop. So that's something you need to pay attention to. So what I'm going to do is very simple. I'm going to create let's see. So it's a pre-existing binary file of homogeneous records, right? That accesses, okay. So we need to access it by index, right? So that means I'm reading from the binary file. So I'm going to create an if stream or if stream. Then I'm going to call it input, right? Because I'm getting input from, and yeah, I'm not using I didn't say using standard namespace, so I have to specify which namespace it comes from. It's from the standard namespace. And then I'm going to say that file, close it at the end of the day. Don't forget to close the file. And then now I'm going to open the file. But open. What file am I opening? What is it called? Remember they said it's water levels dot dat. If we double check, you see water levels dot dat. And then remember that this is a binary file, right? So it's a binary file. So since it's a binary file, I'm going to state the mode, right? What you see, it even shows you some bit of documentation. What open mode is it? So in what mode am I opening it in? iOS. Okay, it's in. I think it's in the standard namespace. It's in the standard namespace. iOS, and then I want to open it in binary mode, right? So I want to open it in binary mode. If you feel like this is too much, you might forget, just say using standard namespace. Keep it simple. I'm just gonna write it like this. You can keep it simple and just come here and say using namespace standard. And then you don't have to specify that iOS comes from the standard namespace. And don't also have to specify that if stream comes from standard namespace. You can write it like that. So just for the sake of simplicity, let's just write it like that. So since I'm working with a vector, I don't have to specify that it's from the standard. And I did say using standard namespace. So whenever I say cout, it knows, oh, this is a cout from the standard namespace. Here we go. Delete. Yeah. So now the code is more readable, right? It makes much more sense. So you open this file. You want to open it in what? Binary mode. And then now you're going to have to read from the file, right? So remember you do input dot read, right? So let's see. Let's just double check our slides. Let me see. That is not it. Polymorphism, nope. Overloading in template, nope. File handling. Okay, so there we go. There's file handling. Okay, there we go. Open that, right? Then yeah, we could read it like this, but there's a proper way of reading it if I'm not mistaken. Let's scroll down. Yeah, don't forget the file flags, these modes. You can open it in binary mode because it was saved in binary either way. So yeah. And then what is it? The whole reinterpret cast thingy. Yeah, I remember what I was talking about. The when you have to do alignment padding, you see, your machine can be 16 bytes, 32 bytes, 32 bit, I mean, or 64 bit. So depending on the system, values are represented differently. So you should make sure it's consistent. Also, what it does, it makes sure that it's consistent. It's like even if you move to another different operating system whereby they use 8 bytes, it's going to be consistent. You're going to have the exact same number of bytes to represent that record structure. So alignment pairing does all of that. So there we go. This is what I wanted. This is what I wanted. So where's the, okay, now it's providing that variable length dot right, reinterpret cost, blah, blah, blah. Also pass the size of the record type. Let me see. Oh, okay, it's actually the same thing. I thought maybe it was different. You don't have to, for the other one, you don't have to pass an array of characters, things like that. So yeah, we're gonna have to do it like this. So we're gonna have to, for both reading and writing to disk, especially if you are dealing with this one. What is this? Okay, this is random access, right? So yeah, but I think we did store it in they did store it run in using random access, right? Okay, let's see. Binary file. Yeah, I think yeah, it has to be random access because here we did that approach, the first approach of reading it line by line. So we have to do this one, reading it from a binary file. Yeah. So when you check your slides, this is the two ways you can read and write from the file. You use the read function and the write function. So it's supposed to take in a string and the size of the data type in bytes. So you can just use the size of operator to get, or the size of keyword to find the size of the operator. So remember, if you remember your slides when they talked about, when we're doing this thing about file handling, remember that it's going to store everything as a string, right? So that's why you have to create a string char pointer. It's somewhere in the slides where they talk about this information. But from the looks of it, I feel like, let me see. I feel like for some weird reason, I feel like, okay, but it's a binary file though. They said binary, so since they said binary, we're gonna read it in that way. We're gonna read it the same way. So since they said binary, we're gonna read it like that. So after reading it, let me see. Let me think how I'm going to. Let me see. I think what I can do is, okay, still fine. I can just do a while loop. Just do a while loop and say, well, input dot eof end of file, and then I negate that. I say while it's not equal. So basically, while I'm not at the end of the file, keep reading, right? Because I don't, and it's a binary file. I don't know how many values are there. I don't know where to start, when to stop. It does know when to start and stop, but I don't know exactly how many values are there. That's the reason why I wrote it like this. And I want to use a while loop, right? So I'm gonna say input dot read, right? I'm reading, and whatever I'm reading, I have to I have to reinterpret it into, I have to cast it into a string, basically character, dimensional array of characters. So maybe char pointer, and then you also take in the size of the dem, right? So what I'm going to do is I'm gonna create, yeah, I was thinking about it. I think I have to create like a vector keep storing to keep storing this information, right? But let me see. Okay, not necessarily a vector. What I can do is I can create um, a variable of type dem, right? And then I call it rec dem, right? Then I do this. So I read from the binary file. And then after reading from the binary, when you're reading from the binary file, store it inside this recdem variable, right? And then after reading, and then also you're gonna need to provide the size of the bytes. Remember what I said. This thing is storing it. It knows where it starts and where it stops in terms of 45 bytes. So it's gonna see, okay, I have 45 bytes here, and then there's the next 45, there's the next 45. So you provided a size, would you, okay, what's the size that you, what size is it, is each record structure of? So that it knows, okay, this is one record structure, and then this is another record structure. So you provide that size. And then remember, when it stores into a binary file, it stores it into a string of characters. It's text. So if, let me see, did it, okay, let me double check something. I wanted to, yeah, there's the executable file. So I want to show you the executable file. So you see, this is the binary file. Remember when we were building this whole time, this is the binary file that it had. You see, it's full of what? Characters. It's full of text. So that record structure that I have, I'm gonna have to I have to cast it to be a text. Remember, this is a binary file. The main.exe is a binary file. You see, it's a binary file. So there's text everywhere. See, text, 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 characters. There's strings everywhere, text. So that's why we have to cast it into, a char pointer. Remember, char pointer is basically a string. But then we just have to do it this way because of C style. We're gonna make it a char pointer like this, and then it takes in, you store that value that you've read from the file into this recdem, and then you pass in the size of the dem in bytes. Then after reading, right, what you're gonna check is gonna check if this counter is equal to the index, right? If it is, then I found, okay, I did that. Okay, let me just leave it like this. So if it is, the counter is equal to that index, then I've found my, okay, yeah, it's fine. Then I found my value, right? Therefore, I can break, I can stop looking, I can stop reading basically, because I found what I'm looking for, right? And then at the end, you're gonna have to increment counter by 1 so that you move on. Remember that this variable counter is going to keep counting. In a way, it's going to mimic the index. It's sort of, we're trying to mimic a for loop, but we don't know exactly how many values are there. So I'm going to create a counter variable separately and then keep incrementing it by 1. And then after reading, I check if this is if count is equal to index that the user is looking for, then you found what you're looking for. Then I stop reading. So it just breaks this while loop, and then it goes out of scope, and then stops reading because there's no point anymore. right? So this is how I would approach it. This is how I would approach it. So we have that. And then now the question is, are we should should we should we like return that accesses the DEM by its index? Okay. Yeah, so it accesses the DEM by index. So therefore I'll just say just return the DEM. Remember, it's supposed to get the DEM. If you remember the accessors that we're creating and doing object-oriented programming, we put the return type here. Get rows, get calls, but it was getting something of type integer. In this case, we're getting back a DEM. So which DEM is it? It's stored inside rec DEM. So I'm just gonna return rec DEM at the end and just say return rec DEM. So this is gonna be version 3.3 or 3.3. And then this is going to be question 2, right? So we have solved it. We've opened the file and then opened it in binary mode because the file is a binary file. Then we created the temporary variable as the temporary variable to store data that we're reading and read from the file. And then it's gonna read. So basically, it's gonna read these bytes. I need to pass it the bytes so that it knows exactly how many bytes to read from the binary file. That's why it was important to do this, to pad it. Because if you go on a different operating system, imagine I'm using a 32-bit operating system, right? And it's saved as, in my 32-bit, it's saved as 48 bytes. Then you go to another operating system, and that operating system in total is going to save it as 68. And then now when it reads the file that you saved on your 32-bit machine, there was only 48. Now it has extra empty spaces. So now there's inconsistencies. It might not even read the data correctly. So that's why you need to package it to be consistent in any operating system. So that if I were to send you this solution or the file, the water levels.dat file, you get the same information. And there's no memory wasted, there's no extra memory, there's no inconsistencies. So yeah, just keep that in mind. And if you're not given the number of record structures to read, you can just use the EOF function and say while it's not, remember the exclamation mark, it means it's not, you're negating. Remember this one returns, it's a Boolean, right? It returns Boolean saying that, okay, true, I am at the end of the file. But then I need to negate that and say, no, if you are not at the end of the file, then keep reading. So obviously this is going to return false, right? Because I'm not at the end of the file. I just opened the file. So it's going to return false. Then the opposite of false is what? True. And remember, while loop only executes when the condition is true. So that's why it's going to work. And then we don't forget to return the DEM that you're looking for. Remember, this was an accessor. It basically it's like you're accessing a value in a two-dimensional array, but in our case, you're just passing one value index. It's sort of like one-dimensional, sort of, but yeah, it's not really that. It's sort of, yeah, it's sort of like that, because when you're passing one index, you're assuming that it's a one-dimensional array. So we have done that. And then now we need to do this one. Write a code for a function that determines if the number of records from a file is odd. I shouldn't have closed those slides. I remember seeing it here. Just this thing is a lot. There's some things that I might forget and not put them in the right structure. But I think you're supposed to add and then you divide by the size of the record structure in bytes, something like that. Mm. Yeah, this is what I was talking about. So C++ makes no distinction between sequential and random access files. So all are treated as streams of characters, bytes. So it treats them as all characters, right? So that's why we had to say to cast it into a array of characters, because it interprets it like that. And then tell G beginning of the file. Mm. Let me see. Yeah, there it is. So yeah, you have to edit and divide by the size of the record structure by the size of it in bytes. Okay, yeah, this function seekg, there's seekg and seekp, if I'm not mistaken. Then there's telg, there's a lot of these functions. So what are we going to do, right? We're gonna, okay, it's actually not a lot, just there's 4 lines of code, right? So you're gonna create a variable that stores the size in bytes, right? First step. So let's say it's gonna return an integer, right? Size in bytes. So get size. I'm gonna call it size. And you're just getting the size. So const. Even this one, we can put const at the end because we just getting it. Oh, okay. It's a non-member. Okay, so it doesn't really matter. Okay, if it's not a member of the class, you don't put that const there. In our case, it didn't care. We didn't have to put it into. You didn't have to put it into a class. So let's look at this function seekg and yeah. So you see, so what seekg does is to move let me see, it's big to the beginning, right? Seek get and seek put methods. We can move the 2 separate position markers around. Okay, I see now. So the seekg, right? Remember that the seekg is to get. So we want to get the records, right? And we also have the because what happens is that C++ keeps track of the current read and write positions separately within a file. So it keeps track of where you are currently reading or where you are currently writing. So what does that mean? So you see this, you see right here, right? There's cursor, the marker right here. If I start typing like this, right, you see it keeps track of where I currently am. Right? Same applies with reading from file and writing to a file. So that's, we're gonna use that to our own advantage, right? So I'm gonna tell it to seek, right? And then it's gonna seek from where? That's the question. You can pass 2 arguments, starting and ending. And there's also seek put, which whenever you are writing to the file, and then tell G, it gets the current byte position. So when you say tell G, you're getting where it's currently at in the file. So for example, you can have this one seekg, right? So it gets the file, or it gets the file from 0 to the end. So basically it seeks from 0 bytes to the end of the file. Basically it's seeking everywhere the file from start to finish. And then, oh, from the end. Okay, it's from the end of the file. So you're starting from the end, and then you can start from the beginning. Or you can start in a current position, but wouldn't want to do current position because we don't know where it is at the moment. Yeah, we don't want to do that in our case. We don't want to do that. So I'm gonna seek get, right? Use seek get, seek G or seek get. It gets the file, and we're gonna start from 0 bytes, starting from the end. You can find the size of the data file, right? So we can start from the end or from the beginning. You can, but just start from the end. 0 bytes from the end. And then when it's done reading, obviously it's gonna seek from the end, right? And it's gonna store the current position in bytes. Then you're gonna get the size in bytes using telg. Then you take that size in bytes, the total, divided by the size of each, right? And then once you get that value, then you divide, you check if it's even or odd, because I think that's what the question was. So when I create a variable, right? So int size in bytes, that's the size in bytes. And I'm gonna initialize it to 0. And then after initializing it to 0, right? Remember that we're gonna have to specify, in our case, we're supposed to specify the file, right? Yeah, you see, we're supposed to specify the file. So I'm gonna have to read the file. I'm gonna have to open the file. Yeah, you're gonna have to open the file, because if you can't open the file, then you can't seek. So you have to open the file. So, okay, I'm gonna just put it on the side. So I'm gonna create an if string and then input, right? Because I'm getting input, and then input dot close. Don't forget to close your file. And then input dot opening the file, called water levels dot depth in binary mode, right? Putting it in binary mode, and then there we go. We have the file, it's opened. So always the cursor is going to be at the beginning of the file. So at the top, at the way the file starts. But yeah, we don't have to worry about that. All I just want to do is just get the size in bytes. So let's get the size in bytes. So obviously I'm going to say size in bytes, and then I say is equals to my file dot seek g, right? It seeks to get the size in bytes. So starting from where? From 0, starting from the end. Oh, then okay, yeah, you don't, what am I doing? You don't store it, you're just seeking first, right? So it's gonna store, basically it's gonna move the cursor from the end to the beginning. So it's gonna move starting from the end, and then it's gonna move to the top of the file, right? To read everything, right? And then after it is moved to, basically this is what's happening here, right? So you see, let me say this is, okay, let me do that. Taken as an example. So I have this, move to downloads, the download folder, quite a lot. So yeah, I'm just gonna create a file called some file.txt, right? then gedit. So I'm gonna edit that file. So there's the file, right? So if you look closely in the file, right, I can start typing, I can do all of that, right? So what's gonna happen is that you're gonna have, this is a file, the best file ever, if that was a thing. But yeah, you see, what's gonna happen is that we're gonna start from the end, but usually it's always there at the beginning. The cursor is gonna be at the beginning. You see this red thing? It's gonna be at the beginning most of the time. But we want it to start from the end to the beginning. So it's gonna keep moving and then count all of the bytes up until the beginning, right? And then once it has moved to the beginning, it's TLG. Remember, TLG stores the current bytes. Remember, if it's currently right here now, and we've moved from the end to the beginning, if we call TLG, which returns the total, returns the current bytes, the bytes of where it's currently at, it's going to return the total because we've calculated everything. If we've moved from the end, we are adding. Every time we move, we're adding, incrementing, and then you get to the beginning. So once we get to the beginning, we now actually have the total size of it in bytes. Then I'm gonna say the size in bytes is equals to input, and then I call till g. Right, I get the total bytes. Right, and then now those total bytes divided by. So remember the question, right? Write a code that determines if the number of records. Yeah. So remember, if I have a total, right? So remember that, let's say, make a simple example. Let's say each thing is represented by the number 10. So if I see the number 10, I know this is a banana, whatever, right? So obviously, if I have, for example, 100, I have a total of 100. How can I find how many bananas are in there? By dividing by the number that each banana is represented by. So if I divide by 10, then I'm going to get 10 bananas in total, right? Because remember, I want to find the number of records. So what I do is I get the total records, and then after getting the total records, I divide it by what each record is represented by, which is like something like this. 10 represents a banana. If I want to find the number of bananas and I have a total, I divide it by what each banana represents, what the number that is represented by each banana, to find the number of bananas. How many bananas are there? How many are there? It's exactly the same thing. So how can I find how many there are? Number of records. How do I find the number of records? I just say size in bytes, write the record, the total, divided by the size of one record. Because remember, remember this is the size in bytes. So if I want to divide by the bytes, I have to use the size to get the bytes of one DEM, so that I can find out how many DEMs are there. So if I find 450, right, and each DEM is represented by the number 45 or 45 bytes. So if I say to find it, I'm just going to say 450 divided by 45 to find how many 45s are in here. Basically, how many DEMs are in 450. Obviously, it's going to be 10 DEMs. And I found exactly how many DEMs are there in my record, in my file, right? After I found how many records, the number is stored in here, right? And they said it should determine if the number of records is from the file is odd, or if it is odd. Okay, so basically it returns true or false. Remember, if it is odd or even, right? So it must return true or false. So I'm gonna make it return a boolean. Basically, I'm gonna return. I'm gonna say call it is odd. If it returns true, then it is odd. If it returns false, then it is even, right? So I'm gonna say return number of records, right? Modulus operator. How can you find something is even or odd? You divide by 2. And if that remainder is equals to 1 or 0, then it's of specific type. If you remember in Maths 1A, or I think it was 1A, so 2K, 2K represents integers, right? It represents even numbers, where K is an element of Z. You remember Z in Maths was integers, right? So K is an integer, so that's the formula. And then 2K plus 1 would represent odd numbers, where K is an element of Z. And 1 is the remainder. So basically what I'm saying is that if a number can be basically if a number is divisible by 2 with no remainder. Why am I saying no remainder? Because here it's basically 2k plus 0. 0 just 0. There's no remainder. So if you divide a number by 2 and you get no remainder, then you know for sure this is an even number. But if you divide it by 2 and you get a 1, then you know it's an odd number. So that's why I'm saying divide by 2. Remember the modulus operator, it gets a remainder. So get the remainder of dividing by 2, this value. If the remainder equals to 1, return true. Then if it is otherwise, return false. That's what this one line of code does. This statement. That's what this statement does. So we have our code here. So yeah, this is the answer for 3.4. Question 3.4. This is the solution for 3.4. And then let's do asymptotic big O notation. So let's do that. Big O notation. So with big O, you must think, what is this? Follow the instructions on the slide. You see. So big O, basically, when you're doing big O, you're just trying to find how fast this algorithm is, basically. Is it in milliseconds, nanoseconds, whatever number of seconds it is? Is it really fast or it's really slow? So yeah, to be honest, whenever you're writing a program, whenever you're writing code, a formula to solve something, you must always check how fast it is, because there's definitely a way faster way of doing it if it happens to be very slow. So it's very important that we do that. We analyze the fastness of an algorithm. So if we check this, the example here, you're gonna have to always write it like this. Obviously, it's gonna be different depending on the number, the code that you're given. If you're given 2 for loops or you're given 1 for loop, it's gonna be different. In our case, we're given 2 for loops, right? But I already know the answer for this code is gonna be O of n squared, because I have 2 for loops, but we'll get to that. So let's continue down here, right? So if we have, okay, not of n, nested iteration. You see, when you have nested loops, it's always gonna be of n squared, as long as you are starting from 0 and you stop at the number before. So basically, like going through each element twice. Remember that this for loop, right, the first one is gonna run n times, right? It's gonna run n times, and then the one within inside of that one is gonna also run n times. So n times n gives you what? N squared. So we're gonna use this approach here, because as you can see, this is how we always gonna have to answer it. So let's see. So assume, we start by assuming, right? So yeah, it's not really nice to have to write it like this, but yeah, we're just gonna have to work with what we have. So I'm gonna make it a multi-line comment. So we're gonna say assume. What are we assuming? So we're gonna assume operators. So we're gonna need to assume operators, right? For operations. So assume what operations or what operators. So in our case, we can assume the assignment, the less than, the post increment, the indexing operator. Yeah, we can assume all of that, right? So I'm gonna need to, yeah, I can only assume with this, it's 1, 2, 3, right? Yeah, 1, 2, 3 is the assignment operator, less than operator, post increment, that's 3, and then 4. We'll just double check if, since I'm indexing twice. Let me see. Yeah, since I'm indexing twice, I just have to double check on that, whether we have to also consider both of them separately or both of them as one thing. So let's see. In our case, in this case, they only had this assignment, you see, equals less than and plus plus, and then here plus just plus plus. In this example, those are the only operators that were there, right? So we're gonna assume that there's operators, right? Assume the operations, right? What are the operators? We said it's the assignment, the less than, plus plus, post increment, and then the indexing operator, right? They measure, provide a fair measure of complexity, fair measure of complexity, right? So we start with that, and then each operation takes the same amount. Let's just make sure that's consistent. Yeah, okay, let me see. Multiplying, okay, we have this, then we also have this. Okay, yeah, we also have to consider them too. Yeah, the stream extraction and the stream insertion is still an operator. It's fair, makes sense. So we also want to consider them. In our case, we have the stream insertion. So because remember, all of these operators are going to be used. That's the thing. We're going to assign here, we're going to use that operator. We're going to check here, this condition, we're going to use that operator. We're going to increment here, we're going to use that operator. We're going to insert into the output stream, we're going to use this operator. So any operator that you know you are using in your code, just make sure you put it there. So I'm also going to put that one there. And then you're just going to say each take the same amount of time to whatever. You just need to know these terms. Same amount of, yeah, it takes the same amount of time. Yeah. And then you need to, let me see, what did this? I think they made a mistake here. Oh, okay. They didn't. Okay, that's fine. So you also need to state what n means. For example, here, What does n mean? It represents the problem size, that basically the number of elements. So we need to also state that. In our case, what does this do? Okay, yeah. So in our case, I would say you write this, you copy this, and you write it in this way. You say, and represents the size, right? And then you specify which variable is it. Let's say it's object right inside that get rows. That's the one that represents the size or the number of elements. So you also need to specify which one represents the number of elements in your in your in your in your in your in your thing in your answer in your answer sheet when you're writing when you're answering this question. So we wrote that. So let T of n represent, okay, it's the problem size. Then you're gonna say let, right, T of n represent the time or the runtime of the algorithm. So it's gonna represent the runtime of the algorithm. So you can imagine T, this capital letter T, just represents time. The time of what to run this problem size or this number of elements. How long is it going to take? And then you also need to state that it contains the doubly nested loop, right? So let's see, T of n. So you also need to say T of n contains a doubly nested loop. So therefore, Tn, now you specify what is Tn. So Tn is basically the number of operations outside the loop, right? So outside the loop, what do I mean? It's, you see here, outside the loop, then inside the loop is going to be this for loop here. It's inside this loop. And then before you get inside this loop, you're going to check outside of that loop. So yeah. I'm just going to say it's equals to the total number of operations outside this loop plus the maximum number of operations inside both loops. That's the formula. So what I'm going to do is I'm just going to be lazy about it and just copy and paste. I can't be typing and typing the same thing. So no, it's wasting time. So for number of operations outside the loop plus the maximum number of operations that it can have inside both of the loops. So basically how many are inside how many are inside this loop, how many are inside this loop, and as you can see, there's nothing inside. So yeah, there won't be anything to write there. So we're gonna have outside, innermost, and outer loop. So let's start with outside, right? For us, how many do we have on the outside? And let's see. For this one, we don't have anything on the outside. As you can see, there's nothing on the outside. We have no assignments, nothing on the outside. So we don't have to worry about that. We could just write 0 there. but still doesn't matter. And then, but yeah, just write 0 there to show that there's nothing outside. Then you're gonna have innermost loop, right? And then the innermost loop. Let's see how you're supposed to structure it. So you're gonna look at the loop header, and then you look at how many there are, and then you look at how many are there in the loop body. Then you times it by the number of iterations. Basically, how many times it's going to run, which is n, because n is the maximum number of times it's going to run. So you can have innermost loop, have a loop header plus a loop body and times maximum number of loops. Basically, maximum number of times it's going to run, which is going to be n times. Because if you check our code, right, it starts at exactly 0 and stops at the number before get rows. Starts at exactly 0, stops at the number before get calls. So these loops are going n times, or object right hand side or get rows times. Remember that we said this is represented by n. N is a way to keep it simple. So let's check innermost loop, right? So I just want to double check something. Yeah, okay. Yeah, this one's way outside, and then we start with the innermost loop, this one. How many are in the loop header, right? If you check in the loop header, it's this one, that's 1. It's this one, that's 2. It's this one, that's 3, right? So it's going to be 3. In our case, it's going to be inner loop. It's this one, 1, 2, 3. So we have 3 operators. I mean, we could. There's something that I'm not including here, but we could also include this one. See this dot? That accessing. That's a member access operator. So you're accessing members, right? So that's an operation. So I forgot to put that there, so we also have to include it. So I'm just going to say the dot there. So in our loop header, we actually have 4, right? Because if you check our loop, right, we have this one. Let me just zoom in a bit. We have this one, the assignment. We have this one. We have the dot that's accessing, that's 3, and then we have the increment, that's 4. But then remember, we start by looking at the innermost loop, this one. So it still applies here. It's 1, 2, 3, 4, right? So that's 4. And then inner loop, the loop body, how many do we have? I have 1, 2. The question is, do you actually repeat or you don't? That's the question. But I'd say it's actually fine. It's actually fine to, I would say it's fine to repeat if I'm not mistaken. Let's just see if they do repeat here. Is there an example where they show? Okay, there's no example here where they show where you're repeating. Let's see. Yeah, there's no example here. There's no, yeah, there's no example. A fair measure. Okay, yeah, I feel like it's actually accurate to do it like that. This is 1, this is 2, this is 3, this is 4. So inside the loop, you actually have, what is this, 4. It's also 4. So it's going to be 4, the loop body. So remember, this is the innermost loop, the one that's inside the loop, times n. So 4 plus 4 is going to be 8 times n. That's going to be 8n. You can just write it on the side here at the end so that you don't forget what the answer is. So we have innermost for loop, right? And then now we also need to take into account this one, the outside. But then the question is, let me see. The question is, does it also count that one on the outside? Let me see. Of n outside is 2. Of n squared. We have outside here, it's 0. Then we go within this one. This is the inner loop, but then we also have outside. They didn't show that example. Let's see. Yeah, they didn't show that example. I don't see the example where the innermost loop shows the outside. So let's see. I want the n squared one. Okay, let's see. Outside is 3, but the outside 3, right? It was talking about this one, these ones. These were the ones that are outside, right? Then you go to the innermost loop. Oh, okay. I think for the outside, right? The best thing you're gonna do, right, for the outside. Maximum operations, innermost loop, blah, blah, blah. Outer loop goes to inner loop times maximum number of loops plus that final answer, right? So I feel like for the outside, right, you should also calculate for this one to the innermost loop too. So you should just, I'm not sure if that's the formula, but that's how I'm seeing it. You're gonna add the ones that are outside this one, the main one, and add it to these ones that are outside the inner one. If you look at ours, we only have 1 on the outside for the inner one. Yeah, 1 on the outside. I'll just say that that's the 1 on the outside. There's gonna be a 1 there. It doesn't really matter. The final answer is n squared. That's the important thing. And okay, this parts you have to have them. These lines where you say these operations or operators, they are a fair measure of complexity. Each takes the same amount and represents our problem size. And then therefore, if n represents our problem size, then T of n would mean how long it takes to run that problem size, right? Then you can also, if you have a doubly nested list, what is this? That doubly nested loop. Sorry about that. Doubly nested loop. You going to also state that you have doubly nested loop. Then you start from the outside. I feel like from the outside, right? What I would say is outer loop as inner loop. Basically, the ones that are on the outside of the inner loop. But it's very tricky. It's very tricky. But let's just keep it that way. So I'm just gonna put that 1 there. The important thing is the of n squared. You don't have to worry about that a lot. So we are done with this. So now the answer that it's going to be calculated as inner loop times maximum number of loops, which is n. That's how we find the outer loop. Outer loop is basically inner loop times maximum number of loops. Basically, the inner loops formula and times the maximum number of times the outer loop is going to run. Remember, the inner loop is 8n. So it's going to be, so the answer is going to be, so it's going to be T of n. What is the inner loops? But you can just, the most doesn't really matter. You can just say inner loop, outer loop if you don't want to make things simple. So the inner loop, what was the answer? It was 8n. So 8n, right, was the answer. But then don't forget to add, shouldn't forget to add the 1 there. Times, say times what? N. So times n going to be equal to 8n squared, right? 8n squared. But don't forget to add the outermost 1. So plus 1. Oh, okay. No. I see now. Let me see. Outer. Okay, no. It's fine. Let's just keep it this way. So T of n, right? So T of n, but whenever you have an algorithm, right? Like this is the final answer, right? 8n squared plus 1. You always drop the constants because either way, if you try to draw this graph, right, these constants are not going to actually change the shape or anything. Just going to multiply it by 8 and then move it by 1 upwards, which is not going to really do much of a difference. The shape stays the same. So since the shape is going to stay the same for the graph, we need to specify all the constants there. There's no need. So therefore, the final answer is going to be the runtime. The algorithm is a complexity of order. So now we're going to say, therefore, the runtime has a complexity of order. Specify the order. The order is O of n squared. Because we drop the constants. They're not going to make that huge of a difference. Imagine just saying plus 1. It doesn't move the graph that much. Even if you say plus 100, either way is still the same. You're just going to drop the constants. They don't change the the thingy, they don't change the shape of the graph drastically. So there's no need for us to have the constants there. So this is how you'd approach 3.5. Yeah, I feel like the annoying thing about 3.5 is having to remember all this assume and whatnot. T represents, yeah, but you just have to write it like that. Then you have therefore as a runtime order of complexity, as a complexity, the runtime is a complexity of order. Then you specify the order. Is it O of 1, which is in constant time, O of n, which is in linear time, because it's going to show you a linear graph, or it's O of n squared, which is going to be, is it quadratic if I'm mistaken? Yeah, I think it's going to be, the O of n squared is going to be quadratic because the graph is going to be a quadratic graph, if I'm not mistaken. But yeah, yeah, that's it. I'm just gonna divide it. Now I'm gonna make a session doing this data structures, right? 2.4, 2.5, and 2.6. So that's it for this session. See you in part 5.